So in the last video, we covered dot products and determinants, and in this video, we're actually going to dive a little bit deeper into dot products, and we're going to be talking about projections. And later, we'll get into how to calculate determinants for a 3x3 matrix. So you might recall that in the last video, right, we covered how to multiply matrices and what they really mean for in terms of transformations. But we also learned about determinants, and we only calculated them for 2x2 matrices. And this is something called a square matrix, because notice how it has the same number of rows as columns. So when you have a square matrix, the number of rows is going to be equal to the number of columns. However, we're going to move on to, let's say this is our 3x3 matrix, and then we will just be calculating the determinant of it, and we will also be looking at the significance of that. All right, so just keep the term square matrix in mind. Now, dot products. We said how it looks like a really simple operation. The way you compute a dot product is it's kind of like the sum when you multiply out the components. So 1 times 2 is 2, 2 times 3 is 6. So the dot product, this is going to be equal to 8. Let's talk about vector components. What do I mean by components? Well, you can see that, vector u and vector v, they're broken down into components. But let's say that vector u, right over here, it casts down like a shadow, right, onto vector v. And so imagine if I'm trying to find out the length of this vector, right? Imagine if I'm trying to find out the length of this vector. That's the component of vector u onto v. Now, a projection would just be the actual vector itself of u onto v. All right, so the difference between a component and a projection is that the component of u onto v just gives you the actual scalar value, but the projection of u onto v gives you the actual vector itself. So the formulas are pretty similar, but they are slightly different. So how do I find out this pink component right over here, the pink length? Well, I know this has an angle theta between u and v, and so imagine if I call this length x. Cosine of the angle theta is going to be equal to adjacent side, which is this x, divided by the hypotenuse, which is vector u, specifically the magnitude of vector u, because we're making this into a right triangle. And so x is just going to be the vector u, the magnitude of vector u, times cosine of the angle. So there we have it. Now, this is going to be referred to using like fancy notation. This is going to be the component of vector u onto v. Now notice how this looks like very similar to what we see in the dot product formula. So recall that the dot product between two vectors is going to be equal to the magnitude of the first vector. So in this case, the dot product between u and v is going to be the magnitude of u times the magnitude of v times cosine of the angle between them. And so looking at this formula, we can substitute magnitude of u and cosine in for the component of u onto v. So I can substitute it into these two terms. And when I do this, I get the dot product is just going to be equal to the component. It's just going to be the component of u onto v multiplied by the magnitude of v. So this is another way to write out the dot product. Now, I want you guys to think about this formula and think about why does this make sense? All right, we're not just memorizing formulas. We actually want to understand why this makes sense. And so imagine if u does not cast a shadow onto vector v. Imagine if these two vectors are perpendicular. That means that u does not have any shadow on v, right? And so it makes sense that the dot product between two vectors, well, this is going to be 0. So 0 times whatever this is just going to be 0. All right, so the dot product between two perpendicular vectors is equal to 0 because you can think about it from a component point of view. When the two vectors are relatively similar, vector u will have a shadow on vector v, and so the dot product will be positive, right? These vectors will be pretty similar, right? And if these two vectors were pointing in sort of opposite directions, the component of u onto v would be a negative value. And so it makes sense that when two vectors are not really pointing in the same direction, right, there's this big angle, big obtuse angle between them, makes sense that the dot product is negative. So everything lines up with what we said about the original dot product formula in terms of the cosine of the angle. But this time we're just thinking of the dot product formula just in terms of the component or the shadow point of view. Okay? Now, the projection formula is a little bit different. So remember that the component just measures the actual like length of this, but the projection is kind of the length, except it's a vector, right? So you want to think about this as essentially the projection of u onto v gives you a vector instead of the component of u onto v. So what I'm going to do is the formula is very, very similar, right? I first find out the actual length of this, the component of u onto v, right? I first find the length of this, and then I'm going to multiply this by the vector v divided by its magnitude. And so you can think about this part right over here as just it's the unit vector in the v direction. So the unit vector in the v direction, right? Remember, when we have a vector and we divide all of its components by the magnitude of it, the length of that vector becomes 1. So you can imagine that, well, you can imagine that what this formula does is that we're taking a tiny step in the v direction, right? This is the unit vector in the v direction, and then we multiply it by the length of the component of u onto v. And so that gives me a vector, that gives me a resultant vector that's the projection of u onto v. So we're essentially just scaling the unit vector in the v direction, okay? Notice how we have a cosine of theta in this term. Well, we can isolate cosine of theta in the dot product formula, and let's substitute everything in. So after I isolated cosine of theta, right, I just divided both sides by the magnitude of u and v. Notice how in my projection formula, the magnitude of u cancels out because that's just a scalar quantity. Notice how the magnitude of v times the magnitude of v is just going to be the magnitude of v squared. So the final formula is very simple, actually. It is just going to be the dot product between the vector u and v divided by the magnitude of vector v squared, right? So the vector v squared. And then finally, you're just going to multiply this by the vector v itself. And so I want you to think about why this formula is still equal to the formula we saw before. Well, the dot product gives me a scalar quantity. And if I divide by a magnitude, that still remains a scalar quantity. And then when I multiply the scalar quantity by the vector v, I still get a vector quantity. And we said how projections give out vector quantities. So everything still checks out. All right. And let me just tell you and save you the math. If you did the same substitution for cosine into the component formula, you'll end up with the component of u onto v is just dot product divided by the magnitude of v. So these are all pretty cool. So now we're going to move on to determinants for 3x3 matrices. So you might recall that when you take the determinant of a 2x2 matrix, it gives you the area of the parallelogram. Or, it could be 0 if it doesn't, have an area. But the point is that it deals with area. So you can imagine that if we have a 3x3 matrix and we take the determinant of it, it gives us volume. And so you can see that the area of something called a parallelepiped, when you have the unit vectors I, j, k, right? So this is just going to be the volume of the cube right over here, right? One unit in I, j, and 1 unit up, the volume of this cube would just be 1 times 1 times 1, which is just equal to 1. Now imagine if I change these coordinates a little bit. So instead of 1, 0, 0, I would have this vector. Maybe let's move it around. Let's move this vector around. Let's move this one down here around. Right? So notice how this gives us a shape, and this shape is something called a parallelepiped. Okay? So your first vector, right, is in the I direction, or it was originally I hat, and then now we transformed it here. The unit vector in the j direction, instead of the unit vector in the j direction, I put the vector in here. So this becomes the second column of the matrix. And then the unit vector in the k direction, I just shifted its coordinates so that now it became this new vector. And so if I take the determinant of those three new vectors that I have, it gives me this volume. And a parallelepiped, notice how it's just like a big, like I just like to think about it as like a big parallelogram. Like, look at all the sides of the parallelepiped. All of the sides are parallelograms, right? So it's nothing really that fancy. It's just a big parallelogram. All right, all the sides are parallelograms. So that's pretty cool. And once again, imagine if our determinant was 0. So this determinant right over here is 0. That means that we have arranged these three vectors such that, well, they form no volume at all, and you kind of compress them into 2 dimensions. So when we think about determinants being equal to 0, we think about loss of information, we think about going from a higher to lower dimension, and so this is exactly the case, right? We go on to from 3 dimensions to essentially 2 dimensions, right? Essentially, this is just going to be, these 3 vectors would just be on a plane, right? We can think about them as being on a single plane that contains them. And therefore, the volume of this parallelepiped would just be equal to 0. So this is an important thing to know. So when you have 3 vectors that are coplanar, and the word coplanar just means that they're all on the same plane. So imagine if I have, this is the x-axis, this is the y-axis, and let's say this is the z-axis. And let's say if I have a plane, right? So you can think about like a sheet of paper. All right. And so if I have 3 vectors that are all on the same plane, right, you can kind of see that, well, they're not going to form any volume at all. And so when 3 vectors are coplanar, their determinant is going to be equal to 0. Now let's compute the determinant of a 3 by 3 matrix. And what better example to do than to compute a determinant that we already know, the determinant of our 3 unit vectors, which we saw created a cube, and the determinant is equal to 1. So we know that. So let's see how we can do it mathematically. So the way you do this is that you kind of use something called like a cover-up method. First thing I want y'all to do, if you're like in a rush for exam, let's say if I'm trying to do this determinant, I'm just going to put a plus minus plus here, okay? The first thing I'm going to do is I'm going to take a look at this 1. And notice how it's in the first row and first column. So first row and first column. So I'm going to place this 1 right over here, right here. And notice how if I kind of cover up the row it's in and the column it's in, notice how I just get a smaller 2 by 2 matrix. And so this is just going to be 1 times the determinant of this smaller matrix. And so next up, this is going to be minus, and I'm just going to do the same trick. My next step is I'm going to, instead of doing this for 1, I'm going to move to 0. And so 0 is in the first row and in the second column. And so this is just going to be 0 times, and then the determinant of what's left behind. So 0, 0, 0, 1. 0, 0, 0, 1. And this is going to be plus, and now I'm going to do the same thing for the last column. So the last column, well, this is in the first row, last column, and so this is just going to be 0 times the determinant of the remaining matrix. And 0 times whatever this is just 0, 0 times whatever this is just 0. The determinant of this 2 by 2 matrix is just going to be equal to 1, and so 1 times 1 gives me that volume of 1, which we saw beforehand, okay? So now we can talk about system of linear equations and how that relates to linear algebra. So system of linear equation. And what better way to start than doing a 2D example? So if I have 2x plus y is equal to 3, and then let's say if I have 5x plus 2y is equal to 4, if I go to Desmos and I graph these lines out, so what did I say? I said 2x plus y is equal to 3, and then I said 5x plus 2y is equal to 4, and the solution to this system of linear equations is just going to be the 2 lines intersection. Now, let me complicate this perspective for you. I can rewrite this system of linear equations into a more complicated format. At least that's what it kind of seems like. So 2, 5 1, 2. So those are the coefficients. And I'm going to matrix multiply this with x and y, and that's going to be equal to 3, 4. Okay? So your first thought to looking at this is, what the hell did I just write? Well, take a look. This isn't actually that bad. We remember the rules of matrix multiplication, right? So if I expand everything out, I get that 2 times x is 2x, and then 1 times y is plus y. And then the second term of this vector right over here is just going to be 5 times x, that's 5x, plus, and then 2 times y. And so ultimately, I get the same result. Right? 2x plus y is equal to 3, 5x plus 2y is equal to 4, except I kind of just written it in like a matrix linear algebra way. Okay, so it's still going to be equal to what I have here. It's just more compact. However, the way that I have this written here, it's really, really weird. So think about what this equation is saying. This is saying that I want a vector xy so that when I transform it through this matrix, it lands on the coordinates 3, 4. Isn't that a really nice way to kind of view this system of linear equations problem? Instead of just 2 lines and an intersection point, now we're defining it in terms of the coefficients, which can be viewed as a matrix transformation, and our final result, which is a vector. And guess what? Let's say if I take my first equation right over here, so 2x plus y is equal to 3, and let's say if I multiply it by 2, so I get 4x plus 2y is equal to 6. And let's say I write a matrix with its coefficients. So it's 2, 4, 1, 2. Notice how if I take the determinant of this matrix, I'm just going to get a value of 0. So it turns out that you can use linear algebra to predict the system of linear equation solutions, the type of solutions that you'll get. If the determinant of the coefficient matrix is equal to 0, you either have infinite many solutions, which in this case makes sense because this is the same line, right? We just multiplied it by 2, or you have 0 solutions. So I'm just going to write this down. Determinant of, let's say, matrix M is equal to 0, then you have infinite many solutions, or you have 0 solutions. And if the determinant of your matrix M, the coefficient one, is not equal to 0, it's non-zero, then there's only going to be 1 solution. And this is at least for 2x2 matrices. You'll see that when we move on to system linear equations with 3 variables, you're able to create, let's say if I have a plane here, and then I have like another plane here, or I'm very bad at drawing this, but the point is that when you're dealing with higher dimensions, there can actually be another type of solution where you have 3 planes and they can actually intersect in a line. All right. Now you might have a little question. Why, when the determinant of this matrix is equal to 0, why do you either get infinite or 0 solutions? And so let me tell you why. So I have this matrix right over here, and so this is 1, 2, and 2, 4. And notice how, since the determinant is equal to 0, everything gets squashed into a line, right? So for any xy point, if I matrix multiply that xy point with the matrix that I have right over here, I'm going to get a value that's on this line. So if I want, so imagine if on the right-hand side, I have a vector that's not on this line that everything collapses to. Let's say if I have, I don't know, -2, -10, like right over here. Notice how there will be no solution to this system of linear equations because any xy point that I have originally, if I matrix multiply it, it's just going to get squished on the line. I'm going to have no solution where, well, the final vector is going to be right up here. Meanwhile, if the matrix is non-zero, notice how there's always going to be some point. And let me just find a better transformation. Notice how when my determinant is non-zero, there's always going to be a point that maps onto the point that you want. So in this case, if I want to map onto this new vector right over here, well, there's always going to be a point that's going to be transformed, and it's going to be able to do that because you're going from 2 dimensions to 2 dimensions. But when you go from 2 dimensions to 1 dimension, if you want a vector as the solution, you're either on the line or you're not on the line. If you're on the line, there's infinitely many solutions. And if you're not on the line, then there's going to be no solution, right? Because there's no way that you're able to take an xy coordinate and map it onto a point that's not on the line after you transform this matrix. There's actually another interpretation for system of linear equations. So if we expand out the matrix multiplication, right? So let me just expand it out right here. So this is just going to be equal to, well, I kind of said it before, but 2x plus y. And then down here, this is going to be 5x plus 2y. And that's going to be equal to the vector of 3, 4, x component for the y component. Now, what I'm going to do is I'm going to break this matrix up into two different vectors. I can say that this big matrix is going to be equal to 2x, 5x plus, and then the second vector has components of y and 2y. And this just comes from, well, the properties of vectors, right? You're able to break the vectors up into kind of smaller pieces because this is the resultant vector, right? Imagine if we added these two vectors together, we would get this big vector because we just add up their components. And now I can factor out an x from this term and a y from this term. So I get x to 5 plus y, and then this is just going to be 1, 2, is equal to, and then 3, 4 here. So what is this equation really saying? This is saying that if I have a vector 2 units and 5 units up, so this is going to be the vector here, and I have another vector 1, 2. So I go 1 unit here and 2 units up. Is there any way to scale these two vectors and add them together so that my resultant vector is going to be 3 units to the left, or sorry, 3 units to the right and 4 units up? So I want a way to scale the first vector and scale the second vector and add them together so that my resulting vector is 3, 4. And that is the third way to interpret system of linear equation. I mean, now that we're talking about matrices, let's just talk about inverse matrices, because might as well, right? So if we define a matrix as essentially a transformation, well, inverse matrix, well, what it does is it reverses that transformation. So if I map, let's see, if I map the coordinate plane, transforming it, is there any way that I can map it back and get back to my original plane? So you can imagine that, like, let's actually get into something called the identity matrix, which is, trust me, I'm telling you, it all seems like a bunch of random terms, but I promise it would all make sense. So we first have to understand the identity matrix. And so the identity matrix has the property that if you matrix multiply identity matrix by A, you're just going to get A back. So it's like the equivalent of 1 if you're considering like multiplication, right? 3 times 1 gives me 3. So 1 would be this identity thing that I'm talking about. And so how do we find out this identity matrix? And I'll first leave it to y'all as exercise. So let's say if I have a matrix like, I'll just keep it simple, 2, 0, blah, blah, blah. Is there any way that I can multiply this by a 2 by 2 matrix so that, well, I get the same matrix back? Is there any way I'm able to do this? And so feel free to try this first on your own, and let's check back. All right. All right, let's see if your prediction was correct. So let's do the matrix multiplication. So I have 2 times A, actually. So this is going to be 2 times A, which is just 2A, and then 0 times D is just 0. And then now I'm going to move on to the first row and second column. So 2 times C is going to be 2C, and 0 times D is just 0. And then now I'm going to move on to the bottom here. So 0 times A is 0, 2 times B is 2B, and then 2 times C is 2C. Or, yeah, 0 times C is 0, and then 2 times D is 2D. Okay. So if I want this to be equal to the matrix on the right-hand side, well, it's pretty obvious what has to happen. A has to be equal to 1. B has to be equal to 0. C has to be equal to 0. D has to be equal to 1. And so if I substitute everything into this upper matrix right over here, you get the identity matrix. So 1, 0, 0, 1. And the easy way to memorize this, and this is for higher and higher, so you can have a 3 by 3 matrix, and this will still apply. All you have to do for the identity matrix is you just have to create a line of ones downstairs, and all the other numbers will just be zeros. So if I have, I don't know, like 1, 1, 1, 1, blah, 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 and then everything else on the sides would just be zeros and everything. So everything else would just be zeros. And you just have a line of ones downstairs, okay? So that's the identity matrix. So I want a matrix so that if I take the inverse of matrix A, so A inverse on both sides, right? I'm going to get the identity matrix is going to be equal to A inverse and then times the matrix A. And this is the equation that we want to solve, okay? So I want a matrix so that if I apply it to my original matrix, I just get back the identity matrix. If this seems really abstract to you, well, think of the multiplicative inverse that you're probably familiar with, right? So for example, let's say if we're dealing with the number 3. Well, the inverse of 3, or at least the multiplicative inverse, is 1/3, because 3 times 1/3 gives me 1, which is, you can think about it as the identity. So the way you can kind of conceptually understand this is that, well, this formula down here is kind of similar to this formula up here, right? Identity matrix is similar to 1. A inverse is like this 1/3 I have here. And this A is our original matrix, aka this 3 down here. So notice how A inverse times A gives me the identity value, okay? And so let me actually just write this out, because I'm just going to include this in because you might see this in like a textbook or something. But let's say if you want like an n by n identity matrix. And so all these are going to be 0. All of this to the right is going to be equal to 0. And then you kind of just do the same thing, right? All of this down here is 0. All of this to the side is 0. And then finally, when we reach this 1, all of the things inside here are 0. All of the things inside here are 0. So this would be an example of an n by n identity matrix. I just wanted to highlight this for you guys because these dots just kind of mean that, well, all of these are just going to be 0. Like, all of these are just going to be 0. Okay? So how do we actually solve for the inverse of a matrix? And we're only going to do 2 by 2 matrices in this video. So finding the inverse of a 2 by 2 matrix, the way to do it for a 2 by 2 matrix is different from the way you do it for a 3 by 3 matrix. It gets a lot more complicated, and you just need a lot more computation to do that. But we're still going to look at that in future videos, but just keep in mind that 2 by 2 matrix, it's actually pretty simple. So A inverse, the way you get it is you're going to take 1 over the determinant of your original matrix, and you're going to multiply that by the adjacent of A, which we'll talk about, okay? So the adjacent of A, let me just write this down real quick. So this is going to be the adjacent of A. If A is defined as just ACBD, well then all you have to do is you flip the 2 on the diagonal, and then you just negate the ones on the other diagonal. And so if we have a matrix, let's say 2, 3, 4, 6, right? Well, the adjacent of that would just be equal to, you flip these 2, so it would be 6, 2, and you just negate the other 2. So it's -4, -3, and there we go. And if we multiply this by 1 over the determinant of this, so the determinant of this is, well, 2 times 6 is 12, and 4 times 3 is -12. Oh no, our determinant is 0. If your determinant is 0, since it's in the denominator, notice how you do not have an inverse matrix. So that's the thing. If you do not have an inverse matrix, well, your determinant is 0. And the way to understand this is, once again, I just love this website. Like, it is so cool. But basically, I think I've talked about this in like previous videos. But if your determinant is 0, notice how everything just gets squashed into a line. And so you're losing information. You're going from 2D to a one-dimensional line. And so there's no way to undo this transformation because information is lost. everything is compressed into a line. All right, so that's the significance of the determinant being 0. This is another one of its significances. Okay, so just as like a little review, when the determinant is 0, right? I think once again I said this in the video before. I recommend y'all watch this if y'all haven't, because I'm self-promoting myself. If the determinant of A is 0, that means that the area of this parallelogram that these two vectors form is equal to 0. That means that if you're having a system of linear equations for, two lines, that's going to give you either infinite many solutions or no solution. And finally, what we've learned here is that if the determinant is 0, you ain't going to have an inverse. So in case you guys are curious where the formula comes from, this is actually an exercise for y'all. All right, so this is the identity matrix, and you know that if you matrix multiply A inverse, which I'll just say has these E, F, G, H, and you matrix multiply that by matrix A with A, B, C, D, right? You can actually solve for the identity matrix. So you can actually solve for A inverse in terms of A, and then what you actually find out is that you're going to get this formula right over here. All right. Note that when you're doing this formula, right, when you look at this formula, note that A inverse comes before A. And this is an important part. You cannot just do A and then A inverse. All right, A inverse has to come first. And what you'll notice is that if A comes first and then you have A inverse, the shapes of the matrices will not be compatible. So that's important. I know that was a lot. Final thing, and we're only going to go into like the very basics of it, the cross product. So the cross product is kind of like the dot product. It's like an operation that you do for two vectors. And the difference is that, well, one of the differences is that the cross product gives you back a vector. So a dot product, you get a scalar quantity. The cross product between two vectors, and you have this cross here, right? Hence why it's called cross product. It will give you back a vector. And so let's take a look at the basics of it. So if we have these two vectors C and B, notice how they form a parallelogram. And the area of this parallelogram, right, is defined right here. Now the cross product, what happens is that you get a new vector that's perpendicular to these two vectors, and the magnitude of this new vector that you get is going to be equal to the area of this parallelogram. So you see how as I make the area of the parallelogram bigger and bigger, you can see that my arrow here, right, the magnitude of this vector, this new vector that I create, gets longer and longer. But the important thing to know is that it's going to be perpendicular. It's going to be perpendicular to the two vectors. So you can see that one vector goes here, one vector goes over here, and as a result, you can see that it forms like a 90-degree angle for the new vector. So the cross product is very, very powerful, because imagine if you're in 3 dimensions and imagine that you have these two vectors and you want to find out the area of the parallelogram that it makes. Well, then that's just going to be the magnitude of the cross product between the two vectors. If you want to find the area of the triangle that it creates, so maybe this will make it better. So this is the parallelogram, right? But if I want to find out the area of this triangle right over here, well, then that's just going to be half the area of the parallelogram. And we said how we can find out the area of the parallelogram by taking the magnitude of this new vector that it creates that's perpendicular to the other two. And in addition, in future videos, we'll also see how planes, so, planes in, 3 dimensions, right? They're actually, cross products are actually very, very closely related to planes. So a plane is actually defined by a point on the plane and a vector that's perpendicular to this plane. And you can see how, well, when we think about something that's perpendicular, you can see how something like the cross product comes in. And you might have remembered that, like, I don't know, maybe your definition of the plane in the past, right? This is also another valid definition, is that it's just defined as 3 points that aren't just on the same line, right? So this defines a plane, but this is another way to define a plane. It's with a point and a normal vector or a perpendicular vector that defines the orientation of it.